everyone. You are in the right place. I'm John from Marco Learning. I'm joined by Gina Ruiz-Houston. How are you doing tonight, Gina?
Just fine. A little excited for tomorrow.
A little excited. I know you're nervous for your own students.
Yeah.
You're based in Florida. Is that right?
Yes, definitely.
Great. Let me know in the chat, everyone, where are you all coming from? I'm live from New Jersey. Gina's live from Florida. We got people all around the world suffering through AP Physics 1 and going through this journey together. It's exciting. We've already had the AP Physics C's earlier in the week. We got Physics 2 on Friday. Our session tonight is going to be focused on Physics 1. This chat is available for you if you have questions, if you have concerns. I don't understand what's going on. Let us know. That's there for you. It's also a place for you to let us know how you're feeling and what you're thinking. And one of the things I want to know is if you would like to see Marco, the founder of Marco Learning, my dog, all 65 pounds of fur. Gina, you've not been on a live stream yet with Marco. So everyone go to the chat and give me a sheep emoji, a cloud emoji, fluffy white blobs of emojis so that we can encourage Marco to wake up from his slumber. This guy is not studying for AP World History. He is not studying for AP Physics, both of which are tomorrow. Let's get the chat lit up. And if you like this video, as we're going through our session, don't forget to press that like button, subscribe to our channel. We have resources in about 15 AP subjects. We have resources in college admissions, SAT and ACT. I'm starting to see clouds and sheeps. And therefore, it's time.
You must wake him.
It's time. Marco, come on.
Must.
Time to go on air. Your fans want to see you. And here it is. Marco, say hi. Give a little blessing to all the AP Physics kids that they might have a nice day tomorrow in their exam. Everyone take your picture, post it on Twitter or on the Instagram or the TikTok. Here he is. So everyone, that's Marco giving you a quick blessing for your exam. Gina, what are we going to review in our session tonight for AP Physics 1?
Well, I first want to hear from them to find out where they are, because I think we're all a little nervous.
Yeah.
Just a little bit. But I did want to kind of just remind us of the different units and how they go together and kind of thinking through what should I do to maximize my score.
Absolutely. So everyone go to the chat right now and let us know what are the specific areas. We're probably not going to get to them all. Remember that we did a live review right here on this channel. Gina did just a couple of days ago for AP Physics 1. So subscribe to our channel to get access to that and all of the resources we have across all of our subjects. So we've got things like, for example, angular momentum. We've got rotational motion FRQs, things like tension, torque, energy, bunch of words. I don't even know what they mean, but they sound smart, man. You guys sound smart. You're already making me feel stupid, which is good. It means that you're smart and ready to get amazing scores. Conservation laws, rotation, force and dynamics, energy, torque, angular momentum, lots of things. So lots of great vibes here in the chat. Everyone, again, if you're enjoying this video, press that like button, subscribe to our channel. Gina, I'm going to turn it over to you to guide us through how to get ready the night before the AP Physics 1 exam.
Okay, sounds good. Okay, I'm going to put up the whiteboard, and I'll say it right now. I do my very best as far as drawing on the computer, so please forgive me if it's not perfect, but I will try. Hopefully, there we are. Okay, now from what I'm hearing, we're all a little stressed, and that's completely and absolutely normal. If you're going into the test and you're not even a little nervous, then I would say get a little nervous so you get those butterflies going and you can really get your brain to start moving. One of the biggest things I would suggest for you today is please don't stay up until midnight. Please do not stay up past your bedtime, okay? Physics is a thinking test. You have to be able to go in there, read the question, think about what's there, and then apply all that knowledge that's in your brain. No two physics questions are identical on any given year. And so you really need to be able to think. Oftentimes on a calculus test, it's kind of formulaic, okay? You'll see this kind, you'll see that kind and such. But physics, they're always new. They're always getting new ones in every year. So you please sleep well so that you can come in tomorrow and you can knock it out of the park. Okay, I know you guys have been studying really hard. Now, it seems like the biggest area for today, it seems rotation. From what I'm looking at, rotational dynamics for you. Okay, so Couple things to tell you about rotation. And my students feel the same way. I want you to think, particularly if you're nervous about it, think linearly. Okay. Think everything I've done. I've done kinematics, I've done forces, I've done momentum, I've done energy. I've done all these things in a linear sense. When we get to rotation, it's kind of just the same thing, but now I'm going in a circle. So don't panic. You actually know this stuff. So I'm going to try to draw. Don't laugh at my drawing. So if you think about it, the velocity that we have for a linear sense, we're going to move it to an angular sense as far as omega, which is an angular velocity. A that we have for linear kinematics, we're going to move to an alpha, okay? And remember that X, that displacement that you've been doing since, well, August? We're going to change that to a theta. So in a sense, we're going to go from our linear sense to our angular sense. So all of those kinematic equations, take the X's and put in thetas. Take the V's, put in omegas. Take the A's, put in alphas. Boom, boom, boom. You got them all. Now, how do I connect them? X is going to be equal to R theta. V is going to be equal, surprise, surprise, to R omega. And A is going to be equal to R alpha. So these are your, in a sense, conversions between your angular and your linear. Now, some of your teachers may have called this S instead of X. That's totally fine. It's kind of old school because when you look at a circle, pretend it's a circle, okay? And that's my radius. The arc length is going to be this piece here. In other words, kind of like the piece of which you're walking along the outside of the earth. So that's why it's called the arc length, is you're going around that outside of the arc. Now, just as you see these happening, that was kind of unit 1, right? Projectiles, kinematics. We then went on to unit 2 and we did forces. So forces, we know the very infamous Newton's second law, F equals ma. Well, that's not possible. I can't make that into a rotating object. Yes, you can. The force becomes torque. The mass becomes inertia, and the A becomes alpha. So here's your linear sense, and here's your angular sense. So again, if you freak out, you're still there. You've got it in your head. Think about momentum. P is equal to mv, right? Okay, what is it angularly? Well, what did I just say about mass? Mass, we change it into inertia. V, what do we change V into again? Omega. Oh. And we call it angular now, momentum. Can you see it? So we're starting to put these things together. So what you have done linearly actually feeds you right into what you're doing angularly. Because the wording, you know, theta, and maybe that one rolls off your tongue, but omega and alpha, maybe those don't roll off your tongue as easily. That's okay. Think of it in the linear term and say, okay, that one's velocity. And then you can normally think through what it is you need to do. May I make one addition, please? Here with torque, not only is it I alpha, but it's also F times L. Do we remember what that is? That's going to be the force times the lever arm. And this is a location, particularly on rotational dynamics, that we tend to go through. And I'm going to write it out if that's okay. I usually write FL is equal to I alpha. Can I do that? Well, yeah, in a sense, I'm saying torque and torque, right? So I'm putting two torques equal to each other. All right, well, force, we know that's some kind of push or pull. Lever arm, your teacher may have written it as L or R for radius, same thing, okay? What was inertia? What did that mean? Let me go back to Newton's first law. An object will stay at rest or an object will stay in motion unless I push it. So think of it as the teenage law. That's how I call it. A teenager will stay at rest or a teenager will keep playing on their cell phone unless mom, dad, or teacher makes them stop. Okay, so that's your inertia. So here with the inertia, we typically have it so that it's going to be some kind of coefficient. I'm just going to put it as a box, mr squared. That's what we're going to use for inertia. Now, I have been, those many years teaching. And way back when I first started, it was physics B, not physics 1. And we had to memorize those inertia formulas. Lucky you, you don't have to memorize them. They'll either give you something, mr squared, or just tell you how much the number is. So yay for you. As far as alpha, they normally don't give it. But how could I figure it out? Look right here. What could I do? Couldn't I solve alpha is equal to A over R? And that's typically what you'll put in. Then what? What is acceleration when we think back to August? Isn't acceleration change of velocity over change of time? Okay. Well, could I write alpha is change of omega over change of time? Isn't this the linear? This is the angular. Can you see what I'm saying? It links directly to it. So you can go ahead and start substituting in here. This R or lever arm can equal this same amount here. And so you can start to play with this formula back and forth, which is kind of lovely. One more thing on this. Hold on, let me get my eraser. I know you love my beautiful handwriting. I try. One thing I want to show you, just because when I was a kid, it used to mess me up. And it's a silly way of remembering it, but it helps. Okay, if you have, let's say, okay, so like a balance beam or seesaw, you know, like for the torque problems. Okay, and you're going to put something, let's say here, and it's going to pull this way. Ooh, that's not straight. And put something here, and let's say it's pulling that way. Okay. How do I know which way is positive? Stupid way, but hold your pen wherever the pivot is and push the way the force is locating. Okay. So if I push here, I'm going to make this go around this way, aren't I? If so, am I going clockwise or counterclockwise? Here I'm going counterclockwise. And if you think of that, physics is kind of like math. Think of a unit circle. This one's going to be positive. Okay. If I change it to the other side, what if I go here? That one's going to be clockwise, and that's going to be negative. Sometimes when you're doing the torques, you have to make sure that you have it both ways and you know how much the positives and the negatives are. Okay, hold on. Can I erase again? Okay, 1 second. All right, for forces and dynamics. Couple of clues. I like green better. Okay. Whatever your diagram is, whatever the scenario is that they've made for you, maybe it's an Atwood machine with a table, a frictionless pulley, some sort of box with a string or rope, and some sort of device here. We're going to call this person A and this person B, okay, or box A and box B. Please remember, look at all of the forces that are there. If I am looking at object B and I draw my free body diagram for B, I'm going to have my weight, correct? And I'm going to have my string. Will I have a normal force on B? No. Normal force infers that somebody is, in a sense, pushing up on your rear end. Okay. There's nobody pushing up on B's rear end. So there's no other force in the vertical. Assuming no air resistance and stuff, we would do a sum. That's how I write sigma. Sorry, it's not beautiful. Sum of forces in my y direction is going to be ma in the y direction. Why am I saying it's in the y direction? Because it's going up and down. Now, who is going in the positive direction right now? Tension. Who's going in the negative direction? I'm going to call it FB just so I can mean it the weight of B. Okay. I haven't said which way this is accelerating yet. Let's look at box A. Okay, on box A, what do I have? Is there somebody pushing up on its butt? Yes. So we will, terrible drawing. We will have a normal force. We will have the weight. Can I call it FA? Is that all right? We're going to have the tension pulling this way. And then there's a question of, in this scenario, do we have a friction opposing or not? Sometimes they give it to you on a frictionless surface. Sometimes they give it to you with a lot of friction on it. So it kind of depends. Let's say we start this with a lot of friction. Will this system move if block A is really kind of adhered to that table? No, it'll be static friction and it will be high and it will just stay like that. If so, this acceleration would go to be 0, wouldn't it? Okay. But what if there isn't a lot of friction, or maybe it's ice? Wouldn't this block tend to go down this way and accelerate? If so, here's where you have the chance of either making down as positive or down as negative. Whichever way your teacher taught you, stay with it. Don't change it now. Stay with it. Okay. One other thing to mention here is, let's say the friction did exist, so I'm not going to put it as a question mark. We would do our sum of forces in our x direction, and we would have ma in the x direction. So it is going to move. We're going to have tension, and we'll have friction, won't we? Okay. In the y direction, we would have ma for block A. Oops. Yeah, can't draw Y. Sorry, which would be normal over the weight of A. Now, would the box sitting on a surface move in the vertical? No, this will sum to be 0. So you're going to end up that normal is probably going to be equal to the weight of A. Why you need that is, look right here. You have friction, and maybe you're not given friction. Remember, friction is mu, the coefficient, times Fn. So we're going to plug this in here. So we're going to have tension minus mu Fn, and now we know how much that Fn is. So that's kind of how you do the dynamics. Now, some teachers teach these Atwood machines as doing the two pieces separate, meaning block A and block B as separate entities, which is kind of how I set it up. Many teachers who are kind of a little bit younger teachers put it as one entire system and have the whole thing moving at one time. Whichever way you learned it, do it. It will come out as the same answer regardless. Okay, forces and dynamics. Got that. Okay. Okay, FRQs in general. Okay, so you know your multiple choice. You're going to have a lot of single response. And on your single response, what I mean is there's some sort of question stem, and you'll have one choice that you get to pick. Remember, though, you're going to have those 5 double responses. So that's considered multiple select. You will have to pick both correct answers. If you do not pick both correct answers, you pick only one of them correct, you do not get partial credit there. It costs as much just as a normal single response one. So if you're good at it, yeah, do it right away. If not, leave it to the end and make sure you got everything else done properly. Okay. In terms of the FRQs, what do we have? Okay. Well, we're going to have a QQT. That puppy is going to be worth 12 points. We're going to have an experimental. That one's worth 12 points. So these are your big guys. Okay. I would say 25 minutes here, 25 minutes here. Okay. Then you're going to have 3 short answers, one of which is going to be your paragraph. Okay. All of these are going to be worth 7 points. The average time should be something in the ballpark of 13 minutes or so. Okay. Now, these are not carved in stone. You don't have to use exactly 13 minutes or anything of that nature. Those are just kind of ballpark estimates. So in other words, if it's a 12-pointer, spend more time on it than you spent on a 7-pointer. Makes sense. Of course, you know this. All right, let's think through it. For the short answer, 2 of them are probably going to be, in a sense, traditional problem kinds of things. Here's a scenario, what do I do? Or even you might have something where, you remember how the workbook, what is it? Angela, Blake, Carlos, and Dominique. Maybe Dominique and Angela disagree about something, justify why one of them is more correct. Or it could be something that's a factor change where, for example, let me show you, think of one off the top of my head. Maybe it's Newton's universal law of gravitation. M1, M2 over R squared. Okay, and what if I say, okay, I am going to move it from Earth that has a radius of R to Jupiter that has a radius of 5R. So now we're at 5R. What would happen to the amount of force? Well, how do I do this? Okay, well, the gravitational constant stays the same, so we leave it as 1. The mass of the space shuttle, whatever moon that's orbiting, stays the same. The mass of Jupiter stays the same, but the radius is now 5R. And that 5R is a square. So what just happened? In a sense, we've got 1 up top and 5 squared in the denominator. So this is going to be 1 over 25 times whatever the original value was. So maybe you have something like that where you're given some sort of math and you do the problem, but maybe part C or D says, now I change blah, 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 blah. What happens? Okay, so that's probably your 2 general short answers. The one that's the paragraph length response, I'm sure your teachers have recited it just like I do, because usually those 7 points, 2 of the points are given to answer the question. So there's 2 points usually at the beginning that say, like, look at the graph or look at the scenario or tell me something. Then it says in a clear, concise paragraph length, explain. Now, for that one, you're going to do most likely claim, evidence, and reasoning. Most teachers teach it this way. Is it the only way? No. But this is what you use in English class, and so that's why a lot of physics teachers do it similarly. Please make sure that you tell us what it is you believe. That's going to be your claim. We're looking for it. It doesn't have to be tremendously long. It could be just 1 sentence, and we're happy. Okay. When you go to evidence, look at the scenario. What is it you see? Okay, I made the radius bigger. Okay, I changed the mass of this. I increased the velocity. What is it you see physics-wise going into that scenario? Okay. Now look at your reasoning. Because such and such changed, or because such and such was related to this, I believe that this is going to be the answer. So in other words, kind of link your thought process, your physics thought process, and put it on paper. Give us that reasoning. Now, you think about writing a paragraph in physics? That sounds so strange. But actually, all we're really asking you for here is to make it apparent to us what's going through your head. So as you look at this scenario, you're thinking different things. Put what you're thinking on paper. So I, as a grader, will look at it and say, okay, they knew that this was happening. They saw that this and this were related. Okay. And if I change this, oh, okay. So I can follow your reasoning. That's how we graders look at your results or look at what you've written. We're looking for those pieces. Now, if you're anything like my students, a lot of us like to put a bullet answer. I do too, but that's not what the AP graders are going to want. They want to see how you think. Okay, so show them what it is that's going through your mind. Okay, so give me the claim, maybe one sentence. Give me the evidence, 2-3 sentences, 2-3 thoughts, maybe 1-2 thoughts. It depends on the scenario. And then give us the reason why that evidence supports your claim. Does that make sense? I hope. Okay. That's worth 7 points. You're guaranteed a paragraph length response. You're guaranteed 2 other short answers. Okay. Now, again, you're kind of thinking English class, I got to write my beautiful paragraph, blah, blah, blah. That's not true. We're not looking as a grader for complete, beautifully written with extra adjectives and adverbs. That's not what we're looking for. Tell me the meat of what it is you're telling me. Okay, tell me what's going on. All right, let's look at the experimental one. Hopefully, in your class, you have done some sort of experimental components. Now, all of us have different COVID issues. So maybe you've been at home for part of the year and in the classroom for others. Or maybe your teacher doesn't have supplies because we don't all have an equal physics classroom. And that's all right. When you get the experimental question, they will say something to the effect of, in a typical physics classroom. In a typical physics classroom, you have things like a meter stick or a ruler. I know you all have your cell phones, so you don't need a timer. It's right there on the cell phone. You have protractors, maybe a couple of masses or something. We're not necessarily saying that you have a probe set. There are some beautiful Pasco probes. There's some beautiful probes in many different types of ones that you can have. There's Go probes that do it straight onto your phone, like a veneer one. You do not have to say that you're using sophisticated equipment. Meter stick, tape, stopwatch on your phone. This is typical. Okay. So it is okay whether you're soup to nuts, whatever price range you're in. Now, don't be afraid of the experimental. If you have done all of your labs online virtually, that's all right, because you've still seen the interaction between different things. If you've done them physically, great. You've seen the same interaction between things. Actually, usually the online ones tend to come out a little bit better than the ones that you do live there in the classroom, but it's far more fun to do it in the classroom. When they are asking you on that experimental one to describe the pieces of equipment, on some of the free responses, they'll give you a table and say, what is the piece of equipment? What quantity are you measuring? And what's the variable or unit for it? So say I said a meter stick, I'm going to use it to measure length, and I'm going to do it in either meters or centimeters. That's not that hard. I can do that. Okay. I'm going to use some masses. I'm going to put them on a scale, or they're going to be already written. It's going to be in kilograms. Okay. I'm going to use my stopwatch or my phone to measure time in seconds. You see what I'm saying? It's not that bad. So if you do have that kind of table on your experimental one this year, you're probably going to get two or 3 points just from the table. What is a probe? Good question. Some schools have probes that will do, like I have one, well, I have 3, not very many. I have a little box that's probably half the size of your calculator, and it's a motion detector. And you connect it to your phone by Bluetooth. And as objects move towards the probe and move away from it, you'll get a motion diagram, like a displacement time diagram on your phone, which is so cool. But I only have 3 and have more students than 3. So oftentimes we'll take a video capture with our phone and measure distances that way. Or maybe you did something with a drop height. Maybe you put a meter stick like this and you dropped a ball and you watched it on your phone and under slow-mo, and you were able to take that kind of data. So a probe of that nature, like a motion detector, I have one that's a force probe. So instead of using a little scale to pull, you pull with this probe and it will measure it on my phone. If you don't have something sophisticated like that, that's totally fine. You can do it other ways. Okay. Different types of functions. I'm not sure I understand the one about the different types of functions of time. If you could get a little bit on that one, and I'll hit the QQT and then I'll come back and answer that one. With the experimental, once you've told me the pieces you're going to use, usually they have you either draw a diagram or tell me the procedure. No problem. Then after that, they may give you some sample data. If they do, go ahead and draw that data on the graph. Now, there is a difference between, and I'm going to write it just to make sure I say it right, a sketch and a plot. What's the difference? On a plot, I want you to actually, go over on the X, go over on the Y, plot the dot, and the next dot, and so on, like you would do for a normal graph in math class. When I'm sketching, I'm doing, yeah, okay, or so-and-so. I have no special numbers. I'm just giving a general idea. Okay. What else? On the QQT, what does that stand for? QQT is quantitative. Quantitative sounds like number. And qualitative is describing. So there are both parts on there. So you're going to have numbers and text. You're going to have to answer in both kinds. You may also have to do it for multiple representations. What does that mean? For multiple representations, you might have a graph. You might also have an equation. You might also have maybe a diagram and things of that nature. So in other words, you're showing it in more than one way. So on a QQT, you're going to have a component of it that's math related, a component of it that's text related, and then usually different representations of the same thing. Now, when I say math here, I'm not saying I'm giving you a number of 40 and 2 and this kind of thing. I'm saying that most likely you're going to have it in variables. If you're lucky, well, from my perspective, lucky, but if you're lucky, probably one of the short answers will be just a traditional physics problem and you work it out mathematically and yay, I'm done. Usually people like those better because I get an answer and I feel better. But doing the same problem with variables is doable. It's just instead of numbers, you get it down to the simplified variables and you call it quits. So most likely you will have it that way. Okay, hold on. I think we got it. Thanks. I appreciate that, Andrew. That's nice. Okay, so second law, summation law. Okay, hold on. Let me just make sure I got that other answer first. Time. Okay. May I erase? Okay. Now, when you are taking this free response section should follow your multiple choice section. You should have somewhere in the ballpark, I think it's 10 minutes, between your multiple choice and your free response. I've never administered the physics test, so I think it's 10 minutes. I'm not positive because I've never administered that one. But on the other AP tests, it's like that. Your brain is working a little bit different for a free response relative to a multiple choice. So remember, when you're looking at multiple choice, you're getting rid of the things that are not possible and picking your best answer. Whereas when you think free response, please slow your brain down just a tiny bit and say, remember, I have to write it down. The person's not inside my head. I must put it on paper. Okay, you must write it there. So I, as the grader, whoever's the grader, can see your thought process. Every little piece that's right in there, we will fight to give you every partial credit point that we can, but we've got to find it on your paper. Okay, we've got to find it. One pet peeve on that. Again, pretend I can draw. Okay. Let's say this is a force diagram. Just pretend. There's your dot. Okay, I'm going to draw my force of gravity here and my force of friction here, but my normal's there. Okay. If I forget to name these, I don't get credit for them. Okay. If I forget to put the butt of this touching my object, I do not get credit for it. Okay. And us graders, we look really hard and we squint our eyes and we say, is it touching? And we try really hard, but you've got to have this touching the object, please. Okay. You've got to have your labels, please. These are some of the easiest points. Please, please, please make sure you're connecting there. Now for weight, you can put FG, some people put MG, totally cool. Okay. Friction, some people put friction or put static friction or put kinetic friction, totally cool. F normal or just normal, totally cool. We're reasonable about such things. We will try to give you those points. Okay. Let me look in the chat. Hold on one second. Okay, there was a question. I will come back to the Newton's second law 1 second. The proportionality in qualitative and quantitative. If it is quantitative, most likely they want you to manipulate it and show it to me. Show me what it should be mathematically. Now that mathematically could be with variables. Technically, you could walk the person through it with words and they could figure it out. Okay, so technically you could do both. When I'm talking about that QQT being qualitative, they're describing more like what would happen if, or there was one recently where they said, you know how they do I and double I, you know, AP loves that. So on I, they said something like a student had this reasoning. Pick the part of that student's reasoning, whether it's statement 1 or 2, that's correct, and tell me why. And statement 1 or 2 that's wrong, and tell me why. Okay, you see what I'm saying? They could also do it with like the student looked up an equation online and found blah, 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 blah. Does that resemble what you have proved in 1 or part A? So there's those kinds of things that you'll be answered. Do we keep the same equation? Yes, you keep the same equation sheet through the whole test. Wow, it didn't used to be that way. Okay, it was only for half of the test many years ago. Now you have the equation sheet and your calculator for the entire test. That is wonderful. They used to also penalize you if you, on your multiple choice, if you put the wrong answer. There is no penalty for putting the wrong answer on a multiple choice. So if it's wrong, it's just wrong. It's not wrong plus something. So it is best to guess if you have to guess. So fill in something on every single one of those multiple choice. Do not leave one blank. Okay, how should we know if we should draw a free body diagram? Okay, if you have, okay, I'm going to try to draw again. Sorry, guys, for my wonderful drawing abilities. Okay, pretend they're straight. Just pretend, okay? And let's say they've given a dot here to represent the piece. They're expecting you to draw a free body diagram. Now, they will ask for it and they will say something to the effect of draw the forces that are on that body without drawing the components, something to that effect. When they have these lines here, they want you to draw it proportionally, meaning whoever's the bigger force should be the bigger vector. So let's say the force of weight is biggest and the normal force is smaller. You need to draw them proportionally to show that the force of weight is bigger than normal. If they're equal, then count the lines and make them equal. Okay, so you need to show that. Sometimes they'll put it on actual graph paper, so they want to see it in the X and Y direction equally. So just be careful there. Where we need to find the phase constant. Okay, hold on 1 second. Let me go back to the free body diagram and I will try to get there too. Okay, let me think of one. Okay. Let me erase for 1 second. What if I have, say, there's my table, and let's pretend here's my box, and I'm pulling here at this angle. I've got weight. I've got normal. I'm sorry, I can't draw straight, guys. I'm doing it freehand on a computer. Let's say friction, and let's say this is my force applied. Ooh, that's really sad looking. Try that again. There, okay. Now, if it is a generic drawing on the side which you're making, you are going to look at this to see that you have an XY coordinate plane. Again, sorry, it's not beautiful. So here, this is my X. Here, this is my Y. Okay. I like to draw it so that we have our sum of our forces in our X direction is MA in the X direction, because that's Newton's second law, right? And we have sum of forces in the Y direction, which is MA in the Y direction, right? That's also Newton's second law. Look at your picture. Who is in the X direction? Well, for us, and it's now not going to be a free body diagram, it's going to be my working diagram. I can take this force apart into its FA in the X direction piece, right? And my FA in the Y direction piece. So in other words, I've kind of done Pythagorean theorem. FA in the X squared plus FA in the Y squared gives me that beautiful hypotenuse. So I'm going to cross this off. This is, again, my working diagram, not my free body. And if I have an angle here, let's call him theta. What is FA in the X direction? Wouldn't that be FA and it's touching? So cosine of theta. And for the Y, wouldn't that be FA sine of theta? True? Okay. So we're going to have MA in the X direction, and we've got two people in the X direction. Who do we have? This guy and this guy. So we're going to put it that we have FA cosine theta minus the friction. Okay. Now let's look at my Y direction. I'm going to change color, maybe pink. Okay. In my y direction, I've got this guy, right? This guy. And I also have this piece, don't I? Oh. So now I'm going to say MA in the y direction with normal up, FA sine theta up, and weight down. Can you see where I took it apart into its pieces? Now, again, that is not a free body diagram. That is my working diagram that I draw on the side, not on their dot on the test. This is how I figure myself out. Now, depending on the scenario, most likely this object is not going to jump off the surface, almost guaranteed. So there's going to be no acceleration in the y direction. So depending on which thing they want you to solve for, move it around algebraically, solve for it, okay? On the x side of the pieces, you might have an acceleration, you might not, okay? If you do, you've got to include it as a number. If you don't include it as a number, because then this whole thing turns to 0. So it depends on the scenario as far as what you get. Okay. Okay. Hold on one. Can I erase for a second? Is that okay? All right. I'm going to erase. I'm going to put this same block now, but in a different sense because, well, College Board, and I like to do it too. We typically don't give it to you just on a flat surface, because a ramp is so much more fun, to have a ramp or a hill that this is on. And that kind of then also brings you back to those Atwood machines. So if I have a ramp, oh, that's good for me. Okay, sort of. I tried. So let's say I put my box or object here. We're going to have an angle for this ramp. And you might have done a problem like this in class. Most teachers, we like to move the axis to be along the ramp is our x, and perpendicular to our ramp is our y. And I'm quite jealous of you because we were not allowed to do this when I was a student. Now, on this one, that's our x and y axis at a rotation. The box is sitting on a surface. So we're going to have, oh God, that's so sad looking. Sorry, I can't draw sideways. All right, pretend that's normal. Forgive me, my lack of drawing ability. Okay. Then we have weight coming straight down. Well, how comes weight's coming straight down and normal's going like that? Remember, the definition of normal is perpendicular to the surface. So if you're sitting this way, it's going straight up. But if you're sitting this way, it's going to go perpendicular, okay? If you're on a roller coaster upside down, it's going that way. So whichever way the surface is pointing, that's the way it's pushing. So it's going to push perpendicular. Notice the weight is going straight down to the center of the earth, at the center of the planet. There is a trick here. This angle of your ramp here is going to be that same angle there in your diagram. Now, yes, you can sit here and do the proof, just believe me, or go do the proof with your math teacher. So we typically in physics will break it apart here, and we will call this part force parallel to the ramp, and this part force perpendicular to the ramp. Notice it's touching here. So this will be FG cosine of the angle, or if you prefer mass gravity, cosine of the angle. This one would be FG sine of the angle, or MG sine of the angle. Good so far. All right. Now, if we say this box is not moving, it's just sitting there. Well, it wants to go that way and fall down the hill, but it's sitting there. So wouldn't friction be going this way to hold it in place? True. So again, same problem, sum of forces in the X, sum of forces in the Y. Who do you see? Okay, in the X, I think I had done orange as X. X direction, don't I have this piece and this piece? So wouldn't I be MA in the X direction, friction going up and mass gravity sine theta going down? Okay. In the Y direction, come back. Y I think I had as pink. Y direction, I've got this guy and this guy. So don't I have MAY equaling normal minus MG cosine theta? Can you see where it's the same problem, just at an angle? Take your time with it. Okay, when you add then a pulley on the end. Oh, that's so sad looking. Oh my goodness. Eraser here. What is happening when we add the pulley? Okay, what's happening is with that pulley, we're going to have usually a string or rope here that is mythical and massless, and usually somebody hanging here. Okay, so instead of friction going in this direction, most likely friction is going to be going in the opposing direction. Most likely it's going to be some sort of mass here pulling this down so that this is going to be pulled up. Please watch the words. This pulley here should be massless and frictionless. If it is not massless and frictionless, it's probably going to be a disk. And if so, you have to include the inertia. And remember, the inertia is going to be some sort of mr squared, depending on what they give you here as the coefficient. It could be a solid cylinder, it could be a disk, it could be a hoop. It just depends whatever they're doing. If you did have a scenario like this, yes, what I've drawn at the bottom there is going to be for this block here. For whatever this block is that's hanging, you'll do tension up and weight down of the object number 2. You'll then start to put the equations together and solve for whoever it is that you need to. Rotational inertia. Okay. When you're talking about rotational inertia, so I'm going to leave the I up there. Think of it like this. We just had the Olympics, right? And so the ice skaters, when they're there on the ice, their arms are out and they're spinning. But man, when they bring those arms in, you can't even see them. They're a blur. So why does that happen? The smaller that R, the faster they rotate. And that's kind of what you're thinking of, is the faster they're going to keep going around. Now, let me mention this. I'm trying to draw a torque. Hold on. Okay, so if the center of the object is here, okay, and let's say I'm pulling force 1 or force 2, okay, will these forces cause this object to rotate? Okay, yeah, they will, because they're going to pull it so that it moves it and rotates it around this way. Okay, you could do your inertia, you could do your torque, and so on. If we have it so that it's pulling straight out, probably not. But if we're pulling it at an angle where I still could get that component, this piece will not do anything for me, but this piece will induce that torque. And so you start thinking about that rotational inertia from where that object is being pushed or pulled. Okay, I have fed you a whole bunch for tonight, and hopefully I've answered just about everybody's question. I'm sure there's more, but I have faith in you. You guys can do this. Please don't stay up much later. Okay, remember, you have to be able to think through what's going on. So read your scenario, read it a second time, make sure you understand what they're asking you for, and then go for it. Particularly on those free responses, make sure you're writing stuff down so any of us graders can look at it and actually see what's inside your head. Okay, so I want you to make sure you think about that. Miss Ruiz is grading me. Miss Ruiz is reading it. I got to write it down or she's not going to know what I'm thinking. So you've got to write it down for me. Okay. All right. Take your time, take a breath. You can do this. You do not have to get every single point on every single question to get a 5. You have to get some points on everything. Okay. So think of it from that perspective. Do your very best and move on. On those multiple choice, an answer on everything, everything. You're not penalized for a mistake. Cool? All right, cool. Knock it out the park, guys. I have faith in you. You can do this. Take care.